Hello everyone. So in this one shot, I'm going to cover alternating current. So I'll cover all concepts, derivation, and important questions that can be asked in your board exams. So let us see the syllabus and then I'll cover each concept one by one. So first we have to focus on alternating currents, like what are alternating currents and how their graph looks like. Then the peak and the RMS value of a alternating current and alternating voltage. Then the concept of reactance and impedance and how different components behave if they are connected with the alternating current source like inductor, capacitor and resistor, right? As of now what we have seen, if we have seen the behavior of these components in a DC circuit, but let's see how they behave in AC circuit. Then the concept of resonance in LCR circuit and then the power dissipation in AC circuits, then the concept of power factor and wattless current, then AC generator and transformers, where we'll see the step up and the step down transformer, ideal and real transformer. So what is alternating current? So we can say alternating current or voltage is said to be alternating if it changes continuously in magnitude. Its magnitude is changing as well as it is also changing direction periodically with time. Now let us see some graphs. So if we have this kind of a graph, you can say the current on the y-axis we have current, on the x-axis we have time. So current is varying sinusoidally. So this is a sine AC current, you can say, right? And in this case, we can say we have a triangular AC and this is a square wave AC, right? And this is sawtooth wave, right? It looks like a sawtooth. So that's why it is known as a sawtooth wave. In this chapter, we will focus majorly on sinusoidal currents, right? Or voltages. And if I want to show a sinusoidal current, I can show it like this. I is equals to I naught sine 2 pi by capital T times small t. Now this is a typical example of sinusoidal current, or I can also write this as I naught times sine omega t, where I naught is the peak value of the current and this omega is the angular frequency of oscillation. So that you have to remember. Now let us see the concept of average and root mean squared current. So if we have given, say, current which is a function of time, if some function is given, let us say it is varying like this, right? And we want to find the average value of this current from 0 to, let us say, capital T, right? So capital T is, let us say 0 to capital T is the interval. We want to find the average value. So what are we going to do? So the average value, we can show it with this sign of this current from 0 to 2 will be the area under this graph, which will be f dt, because this is the time axis and this is the function, right? From 0 to t divided by the interval, so t minus 0, right? So that you can remember. So if we have given a graph, the area under the graph divided by the duration will give us the average value of that function. Now let us see if we have given a function as I naught sine omega t. Now in this case, the time period is 2 pi by omega. And let us say we want to find the average value of this function in 0 to t by 2 in half of the time period. First, let me plot the graph. This is I and this is t. It's a sine function. And we want to find the average value from 0 to t by 2. And do remember this, in case of a sinusoidal function, the area under the graph will be 0 for a complete cycle, because this will be positive area and this will be the negative area. So the average value of a sinusoidal function will be 0 in one complete cycle. So we have to find, in this particular question, we have to find the average value in half cycle. So what we can do, so we can say the average value in half cycle will be integral I dt from 0 to t by 2 divided by the duration, so t by 2 minus 0. So let us integrate this. So integral I naught sine, so I can write omega as 2 pi by capital T times, right? 2 pi by capital T, and from 0 to t by 2. Now it is a quite basic integration, right? The integration of sine is minus cos So I can take the constant factors out of the integration. So the average value of current will become I naught divided by T by 2, and the integration will be minus cos 2 pi by capital T times small t divided by the coefficient of t. So 2 pi by capital T. So that is the integration of sine 2 pi t upon capital T. So it and the limit is from 0 to t by 2. So this will be 2 I naught by t, and we have 2 pi in the denominator, and then there is a t in the numerator. Let us put the limit. So minus cos 2 pi t times t by 2 plus cos 0. So this 2 will get cancelled out, t will get cancelled out. So we have I naught by pi, and here t will get cancelled out, and this 2 will get cancelled out. So we have minus cos pi, and cos pi is minus 1. So minus times minus 1 is plus 1. So and cos 0 is plus 1. So it becomes 2. So do remember that 2 I naught by pi is the average value in half cycle. So if we have given voltage, let us say V as given as V naught sine 2 pi by capital T times small t, the average value of this function over one or over a half cycle will be 2 V naught upon pi. So that you can remember. Now let us see the concept of root means RMS value, right? And RMS stands for root mean squared value, right? Root mean squared value. So RMS current, what is RMS currents? So we have given I as a function of time. Root mean squared. It means you have to square the function, take the mean, and then take the square root. So first you have to square the function, then you have to take the mean, that is the average of that, and then you have to take the square root. So do remember these steps. So if I have given function I, which is, so I is given as I naught sine 2 pi by capital T times small t. Let us, this is our function, and we want to find the RMS value of this function over complete cycle, over one complete cycle, means from 0 to capital T, where capital T is the time period of one oscillation. So what we're going to do, we'll square this. So first let us square this. So this will become I naught square sine square 2 pi t upon capital T. Now we're going to take the mean of this. So how we can find the mean? So mean will be integral I square dt from 0 to t upon interval, right? Now this is the average of I square function. So let us simplify this. So this comes out to be I naught square will come out divided by t integral sine square 2 pi t upon capital T times dt from 0 to capital T. Now how to solve sine square integration? So we can convert sine square into, you can say, cos, right? So we know that cos 2 theta is 1 minus 2 sine square theta. So sine square theta can be written as 1 minus cos 2 theta by 2. So we can use this identity to solve this integration. So this can be written as I naught square by t, and this can be written as 1 minus cos 2 theta, right? So here we have sine square theta, so we can write it will be cos 2 theta. So this will become 4 pi t divided by capital T and divided by 2. Now we can integrate this quite easily. So this will become I naught square by t, and there is 2 in the denominator, integral dt minus integral cos 4 pi t by capital T dt from 0 to capital T is from 0 to capital T. So this is I naught square by 2t, and this integration is nothing but t. So minus, and the integration of cos is sine, right? sine 4 pi t upon capital T divided by the coefficient of t, that will be 4 pi by capital T. And the limit is from 0 to t. So this will become I naught square by 2t, and this comes out to be t minus t by 4 pi. And let us put the limits. So first we have sine, if you put t, it becomes 4 pi minus sine 0. Sine 4 pi is 0, sine 0 is also 0, right? So we can say this is nothing but I naught square by 2t times capital T. So it is I naught square by 2. So this is the average value of I square function. Now the RMS value will be root of I square, this average value of I square. So this will be I naught by root 2. So that you can remember. So this is the RMS value of a sinusoidally varying current. So I naught is the peak value, and divide this by root 2, you will get the RMS value. So do remember this. And if you have seen the voltages that is being supplied to our household, we have seen 220 volts, and that 220 volt is the RMS value of the voltage. So peak value will be, so if we have 220 volts, if I multiply this with root 2, we will get the peak value. So peak value comes out to be 313 volts, right? So that you can remember. I hope the concept of average and RMS value is clear to you. Okay, right. So let me write one more important thing. If we have given a sine function, right, its average value of one complete cycle is 1 by 2, that you can remember. And if we have a, say, cosine function, its average value over a complete cycle is 1 by 2. Sorry, square, sine square function, its average value is 1 by 2, and cos square function, its average value is 1 by 2. And if we have a sine function, its average value is 0 for complete cycle, and for cosine function, its average value is 0. So if you have a question like this, I is, say, I naught sine omega t plus I naught cos square omega t, right? Something like this. And we want to find the average value of this. So what are you going to do? You will take the average value of both the terms. So average value of this I will be average value of the first term times the plus average value of the second term. I naught will come out. So what is the average value of sine omega t over a complete cycle? That will be 0. And the average value of cos square function will be 1 by 2. So this will be 0, and this will be I naught times 1 by 2. So we can say for this particular function, the average value will be I naught by 2. Okay, let me give you one more example. If we have given I as a sine omega t plus b cos omega t, and we want to find what is the average value of this function, or let us say we want to find the RMS value. Let us first find the RMS value. So to find the RMS value, first we have to square this. So it will be a square sine square omega t plus b square cos square omega t plus 2ab sine omega t cos omega t. Now here 2 sine omega t cos omega t is sine 2 omega t. So this can written as a square sine square omega t plus b square cos square omega t plus AB times sine 2 omega t. Now we have to find the average value of this. So let us find the average value. So we have to find the average value of all the terms. So let us take the average value of all the terms, right? So we have a square will come out. So we have average value of sine square omega t plus b square will come out, average value of cos square omega t. Then AB will come out, average value of sine 2 omega t. So if we have a sine function, we know that the average value of one complete cycle will be 0. So this term will become 0. The average value of cos square function is 1 by 2. So this will become b square by 2. And the average value of sine square function is 1 by 2. So this will become a square by 2. So that is the average value of I square function. Now to find the RMS value, we have to take the square root. So RMS value will be root of I square, average value of I square. So that will be root of a square plus b square by 2. I hope the concept is clear to you. Right. So now let us see some illustration. The peak value of EMF in AC is E naught, right? It's RMS value. E naught is the peak value, so RMS value will be E naught by root 2. Average value over a complete cycle will be 0, and the average value of over a half cycle will be 2 E naught by pi, right? So this is for complete cycle, and this is for half cycle. Now let us see another question. Distinguish between the term average and the RMS of an alternating current that we have already discussed. The instantaneous current from an AC source is I equals to 5 sine 314t ampere. What is the average and the RMS value? Okay, right. So we have given I as 5 sine, and this 314, I can write this as 100 times 3.14, which is 100 pi, right? So 100 pi t. So its RMS value will be nothing but peak value. 5 is the peak value divided by root 2. And its average value over a complete cycle is 0, right? And its average value over half cycle will be 2 times 5 by pi, because we have seen this formula 2 I naught by pi, right? That is the average value over half cycle. So this will become 10 by pi, and this will be in amperes, right? Now let us see a very important concept, a concept of phasor. Let us say we have given an alternating current. I is I naught sine omega t, right? So if I represent this sinusoidally varying physical quantity with a vector, let us say this is the reference line, and there is a vector, and the length of this vector is same as the peak value of this function, right? So the length is I naught, and this vector is rotating with an angular velocity which is same as the angular frequency of this physical quantity, which is omega. So it is rotating with omega. So in time t, the angle made by this vector with the x-axis or the right direction will be omega t, right? Because theta is omega t. So if I take the projection of this vector in the vertical direction, so what is that projection? Let us see. So this is the projection. So that will be I naught sine omega t. And this is nothing but this function only, right? So we can say if I represent a physical quantity which is varying sinusoidally with a vector which is rotating with the same angular velocity, which is the angular frequency of that physical quantity, then the projection in the vertical direction will give us the instantaneous value of that physical quantity. So I naught sine omega t is the instantaneous value, I naught is the peak value. So do remember this, it is very important concept. We're going to derive majority of the formulas by using phasor concept. Let me give you one more example. Let us say there are two currents. I1 is say I naught sine omega t, and there is another current I2 which is I naught sine omega t plus pi by 6. So it means the phase of I2 is ahead. So basically this is known as the phase, right? Omega t plus pi by 6 is the phase of I2, and omega t is the phase of I1. So what is the phase difference between the two? It is pi by 6. So if I show this on a phasor diagram, this representation is known as the phasor diagram. So if I show I1 as like this, right? I1. The phase of I2 is pi by 6 ahead. So I will draw I2. This basically this is the I1, and this is the peak value of I1. And I2 I can show it like this, where this angle is pi by 6 and this is I naught. So we can say this is our I1 phasor, this is our I2 phasor, and both these phasors are rotating with the same angular velocity omega because they have the same angular frequency. So the angle between these two phasors will never change. It will remain same as pi by 6. So with this we can find with this we can represent how the two physical quantities are related, which one is ahead, which one is lagging behind. Okay. Now let us see the behavior of different electrical components when they are connected with alternating source. So first of all, let us see what is an alternating source. So we can represent an alternating source with this symbol, and we can say E is equals to E naught sine omega t, where E naught is the peak value of this source and E is the instantaneous value of the voltage, right, provided by this source. And omega is the angular frequency of oscillation. Now let's see what happens if we connect a resistor to a alternating source. So there is a resistor and it is connected with an alternating source, and we have given E as E naught sine omega t, and the resistance is R. Let us say at time t the current in the circuit is I. I is the current. So if you apply KVL, right? If you apply KVL in clockwise direction, we can say E naught sine omega t should be equals to I times R, where I is the instantaneous current in the resistor. So we can say I can be written as E naught by R times sine omega t. So current, so the phase of the current is omega t, and the phase of the voltage applied across the resistor is also omega t. So we can say there is no phase difference. And this term E naught by R can be written as I naught. So in case of a purely resistive, if we have only a resistor in a circuit, we'll call it a purely resistive circuit. So this is known as a purely resistive circuit. And in purely resistive circuit, there is no phase difference between the voltage applied to the across the resistor and the current which is passing through the resistor. So we can say E and I are in phase. When they are in phase, there is no phase difference. And peak value we have seen I naught is E naught by R. And if I want to show this on a phasor diagram, so if this is E naught, then I naught is also in the same direction, because there is no phase difference. So there will be zero angle between these two phasors, and both these phasors are rotating with angular velocity omega. And if I want to show this on graph, we can show it like this. This is I or E, right? And here we have, let me show E with red color, right? And on the x-axis we have time. So let us say this is current through the resistor, and this value is I naught. Similarly, we can show the voltage. This is the voltage applied across the resistor, and this peak value is E naught, right? So that you should remember. Now let us see some questions. So an alternating voltage given by V equals to 140 sine 314t is connected across a pure resistor 50 ohms. Find the frequency of the source. Okay, right. So we have given source as V equals to 140 sine 314t. And we know that if we compare this with this, E is equals to E naught sine omega t. So this omega is nothing but 314. So the fr angular frequency is 314 second inverse, or I can say this is nothing but 100 pi second inverse. So what is the relation between frequency and angular frequency? Angular frequency is 2 pi times the frequency. So frequency will be omega upon 2 pi. So omega is 100 pi and divided by 2 pi, so we'll get 50 hertz, and frequency is in 50 hertz. So that is the answer of first part. The RMS current through the resistor. So for the second part, peak value is given as 140 volts. So RMS value will be 140 divided by root 2. So that is the RMS value. Okay, right. So now let us see what happens if we connect a capacitor across a alternating current source. So there is a capacitor of capacitance C and it is connected with a alternating current source. And again, I'm taking the voltage of the source as E naught sine omega t. Okay, let us say at time t the current in the circuit is I and this plate has a positive charge and this is negative charge. So we can say the voltage across the capacitor will be same as the voltage of the source. So it will be E naught sine omega t should be equals to, and the voltage across a capacitor is what that we have studied in DC circuits. So Q is equals to CV. So from here we can find V as Q by C. So that will be Q by C. So from here we can say Q is equals to C times E naught times sine omega t, right? Now this is the instantaneous charge on the capacitor. If I want to find the current in the circuit, we know that the current will be given by dq by dt, the rate at which the charge is being increased on the capacitor. So current will be dq by dt. So if I differentiate this, ce naught is constant. Differentiation of sine is cos, and since the coefficient of t is omega, we have to multiply with omega. So it will be ce naught times omega cos omega t. And this can be written as E naught divided by 1 by omega c. And cos omega t can be written in terms of sine as omega t plus pi by 2. So that is the instantaneous current in the circuit. And this value, which is the factor, this value is nothing but the peak current. So I naught is E naught divided by 1 by omega c. And this denominator 1 by omega c can be written as Xc, which is known as capacitive reactance. Now capacitive reactance is is the resistance offered by the capacitor to the alternating current. So we can say Xc is 1 by omega c, and if I plot the graph of capacitive reactance with angular frequency, it will be decreasing with the increase in frequency. That you should remember. And the unit of Xc is nothing but ohms, right? It is measured in ohms. So it is just like a resistance offered by the capacitor to the alternating current. So that we should remember. And one more important thing you have to remember is in this case, the current is leading the voltage by pi by 2. So I leads E by pi by 2. Or we can write this as E lags I by pi by 2. So what you can remember, whenever we have a capacitor, then the voltage across the capacitor will lag by the current by pi by 2. That you should remember, right? So I is the current, E is the voltage across the capacitor. So if I want to show this on a graph, let us see. So I and E with a red color. So which one is leading? Current is leading, right? Sure. Okay, right. So current is leading, so and it is a cosine function. A physical quantity which is leading will attain its maximum value first. So can you see the current has already attained its maximum value as soon as we have started the graph, right? So current, sorry, this is, I should draw this with black color because this is current and I've taken black color for current, right? Now let us see for the EMF, and this is for the EMF, right? So I hope this concept is clear, and let me draw the phasor diagram. So here we have, let us say this is E naught, right? and the current is leading by 90 degrees. So I can show it like this. So this will be I naught, and the angle between them will be 90 degrees, and I is leading and they're rotating in the anti-clockwise direction. And if we have only capacitor in a circuit, such circuits are known as purely capacitive. And a purely capacitive circuit, the current leads voltage by pi by 2. Right. Now let us see what happens if we have an inductor in the circuit. So there is an inductor of self-inductance L, and it is connected with a AC source. And this AC source has a EMF E naught sine omega t. And let us again assume that at time t, the current in the circuit, instantaneous value of the current is I. And this, let us assume this current is increasing. If this current is increasing, then we know that this end will be at high potential, this will be at low potential, and the voltage drop across the inductor will be L di by dt. So L di by dt. So we can say E naught sine omega t will be equals to L di by dt. Now from this we can say di by dt is equals to E naught by L sine omega t. Now that is the current. So if I want to find the current value, then we can say it will be di is equals to E naught by L sine omega t times dt. Now what we're going to do, we'll do the indefinite integration, right? So this will become I, this will become E naught by L. The integration of sine is minus cos. So minus cos omega t divided by omega plus some constant. So we can say I will be E naught by omega L, and minus cos omega t can be written as sine omega t minus pi by 2 plus C. So we have a alternating EMF source, right? And that alternating EMF source can sustain only alternating current. So this C has to be 0 to make this current sinusoidal, right? So C has to be 0 because an AC source can only sustain alternating current, right? If C is non-zero, in that case, we can have a case where I is non-oscillate, or where I is not alternating. It can be having one sign only, right? Positive or negative. So we can say I will be E naught by omega L sine omega t minus pi by 2. And if you look at this vector, this is nothing but the peak current. So I naught will be E naught by omega L, and this omega L can be written as XL, where XL is nothing but the inductive reactance, and this inductive reactance is just like a resistance offered by the inductor to the alternating current. So we can say XL is having value omega L, and if we plot the graph, on the y-axis we have XL, on the x-axis we have omega, so it will be a straight line. Got it? And the slope of this straight line will give us the inductance, self-inductance value. So this is theta. So tan theta will be L. Okay, now let us draw the phasor diagram. So if you look at the phase of the current, so it is omega t minus pi by 2. So we can say the current is lagging behind the voltage by pi by 2. So we can say I lags E by pi by 2, or we can say E leads I by pi by 2. So let us draw the phasor diagram. So if this is E naught, then I can say this will be I naught, because and it is lagging behind E naught by pi by 2. So if we show this on a graph, So I with black and the voltage with blue, with red. So if I show the current, so current is like this, right? Negative cos. And this value is I naught. This is minus I naught. Now let us show sine voltage. So that will be this, right? So now let us see the illustration. So in this question, we have given two graphs. On the y-axis, we have given opposition to the current, and on the x-axis, we have given frequency. So this is for circuit element X, and this is for Y, and we have to compare. We have to find like what is X and what is Y. So opposition to current is nothing but the resistance, right? So here the opposition, or you can say the resistance, is not changing. So we can say this is for a resistor, because resistance does not depend upon angular frequency or frequency of oscillation, right? And in this case, can you see the opposition is decreasing with the frequency? So this is basically a capacitor, because in case of capacitor, capacitive reactance is given by 1 by omega C. So as omega increases, reactance decreases. So Y is, you can say the circuit element Y is capacitor and circuit element X is resistor. Right, so now let us see what happens if we have, say, two components in a circuit connected with a AC source. So first we'll see LR circuit. So in LR circuit, we have an inductor and a resistor connected in series, and right, with a AC source. And let us say the voltage or the EMF of the AC source is given by this E naught sine omega t. And let us say at time t, the current in the circuit is I, and the instantaneous voltage across the inductor is VL, and the instantaneous voltage across the resistor is VR. Similarly, the peak value or the maximum value of VL is VL naught, and the maximum value of VR is VR naught, and the maximum value of I is I naught. And we have studied that the current lags voltage in case of a inductor, and there is no phase difference between the current and the voltage across the resistor. So I can show it like this. So I can say I lags VL by pi by 2, and no phase difference between I and VR. So that we can remember. So let us plot, let us first draw the phasor diagram. So to draw phasor diagram, we'll use the peak values of the voltages and the current. So let me first draw I naught. So this is I naught, that is the peak current in the circuit, and in the same phase we have VR naught, and the current is lagging behind the voltage VL. So we will show VL like this. So this is VL naught, right? Now the resultant of these two, so we can say the vector E will be nothing but the vector addition of VL vector and VR vector, right? So if I find the resultant of these two vectors, this will be E naught. And the phase difference or the angle between E naught and I naught is nothing but the phase difference between current and the voltage supplied by the battery or the AC source. So from here we can say tan phi will be VL naught by VR naught. And what is VL naught? It will be peak current times the inductive reactance, and VR naught is peak current times the resistance. So this comes out to be XL by R. Now from this equation we can find the phase difference between current and voltage supplied by the AC source. Now if I want to find the current, peak value of the current, so we can use this right angle triangle, right? So we can say E naught square will be equals to VL naught square plus VR naught square. So if we substitute VL naught and VR naught in terms of peak current, we will get I naught as E naught divided by root of XL square plus R square. So this is the value of peak current, and the denominator is known as reactance, or you can say impedance, not reactance, impedance, right? And impedance is just like a resistance offered by the series combination of LR to the alternating current, and it is denoted with Z. So it will be root of XL square plus R square So you should remember this formula also. So if I want to write the want to write the instantaneous current, instantaneous current will be I naught sine omega t minus phi, because current lags E by phi, right? And if I want to write the instantaneous voltage across the inductor, it will be I naught sine, oh sorry, it will be V L naught sine omega t, and this angle between E naught and VL naught is pi by 2 minus phi. So this can be written as omega t plus pi by 2 minus phi. Similarly, if I want to write the potential instantaneous voltage across the resistor, that will be VR naught sine omega t minus phi. I hope it is clear. So we should remember, in this case, the current is lagging behind the voltage with an angle which is less than 90 degree. Such circuits are known as inductive circuits. So it is a inductive circuit. So that we have to remember. Now let us see a question. So an AC voltage 100 volt and 50 hertz frequency is connected across a 20 ohms resistor and 2 millihenry inductor in series. Calculate the impedance and the RMS current of the in the circuit. So here let me draw the diagram. So we have a 20 ohms resistor and there is a 2 millihenry inductor, and it is connected with the AC source. And if parameters of the AC source are given like this, then this is the RMS voltage. So ERMS is given as 100 volts and frequency is given as 50 hertz. So if you want to convert frequency into angular frequency, we have to multiply this with 2 pi. So that will become 100 pi second inverse. So now we know omega, right? We know the inductance. So, and the impedance. So before, in the first part, we have to calculate the impedance. So impedance is for LR circuit is given as root of XL square plus R square. And what is XL? It is omega times L. And omega is 100 pi. And L is given as 2 millihenry. So it will be 2 by 1000, right? So this comes out to be pi by 5 ohms, right? And R is given to us as 20 ohms. And if you substitute these values in the formula, so we have pi by 5 square plus 20 square, right? Now pi by 5, square of pi by 5 will be very small. So you can say it will be something like pi square is nearly equals to 10 divided by 25 plus 400. Now this 10 by 25 is negligible in comparison to 400. So we can say it is nearly equals to 20 ohms. And we have to find the RMS current in the circuit. So ERMS will be ERMS, okay, right. RMS current in the, so this will be IRMS will be ERMS divided by the impedance. So it will be nearly equals to 100 divided by the impedance, that is nearly equals to 20. So this will be nearly equals to 5 volts. Sorry, not 5 amperes, right? Not volts. Now let us see the next question. An inductor L of inductive reactance XL is connected in series with a bulb B and an AC source. So there is an inductor and it is connected with a bulb and there is a AC source. So they are connected in series. How would the brightness of the bulb changes when the number of turns in the inductor is reduced? So first case, when we reduce the number of turns, we know that self-inductance is mu naught n square times A. The last video, it is directly proportional to the square of the number of turns. So as we reduce the number of turns, L will reduce. As L reduce, inductive reactance, which is nothing but omega L, will also reduce. If this reduces, we can say the impedance, which is root of XL square plus R square, this will also reduce. As impedance has reduced, the current in the circuit or the peak value of the current will increase, because current is inversely proportional to the impedance. So I naught will increase. So as current increases, we can say the brightness of the bulb will increase. So in the first part, brightness will increase. Brightness will increase. Second, an iron rod is inserted in the inductor. So when we insert an iron rod, which is a magnetic material, the inductance, since you can see the inductance, it is directly proportional to the permeability. So the permeability will increase. So inductance will increase. So in second case, L will increase. So XL will increase. So impedance will increase. So current will decrease. As current is decreasing, brightness will decrease. So we can say brightness of bulb. Third case, a capacitor of reactance XC equals to XL is inserted. Okay, right. So we'll do this part once we are done with series combination of X and L. Once we are done with LCR circuit. Okay, so I'll come to this later. Now let us see what is an RC circuit. So when we have a resistor and a capacitor connected in series and we have connected them with a AC source, which is E equals to E naught sine omega t, and this is R and this is C. Let us say I is the instantaneous current. So if I draw the phasor diagram, and let us say this is the instantaneous voltage across the resistor and this is the instantaneous voltage across the capacitor. So we can say VR and I are in phase, and in case of a capacitor, the current leads voltage by pi by 2. So we can say I leads VC by pi by 2, right? So if I draw the phasor diagram, so we can say this is I naught and this is VR naught, and current is leading, right? So we can show VC naught like this, right? And the vector addition of VL naught, VR naught and VC naught will give us the peak value of the voltage applied by the battery or by the AC source. This is E naught. Now, what is the angle between E naught and I naught? It will be phi. So this is the angle. So from here we can find tan phi, which will be VC naught upon VR naught. And VC naught is I naught times the capacitive reactance and VR naught is I naught times the resistance. So that will be XC by R. So if I want to find the peak value, so we can say VC naught square plus VR naught square is equals to E naught square. And from here we can find the peak value as E naught by root of XC square plus R square. Now the denominator is nothing but the impedance of this circuit, or this is the impedance. So Z is root of XC square plus R square. And since XC is inversely proportional to angular frequency, as the angular frequency increases, XC will decrease, so the impedance will decrease. So if I want to show the current, I will be I naught. Since in current is leading omega t plus phi. It is leading by phi. And if I want to show VR, so this will be VR naught sine omega t plus phi, right? If I want to show VC, it will be VC naught sine omega t minus pi by 2 minus phi. Because this angle is pi by 2 minus phi. Right? So in this case, current is leading the voltage, but by an angle which is less than 90. So such circuits are known as capacitive circuit. Capacitive circuit. I hope this concept is clear. Now let us see some illustrations. A lamp is connected in series with a capacitor. Predict your observation when this combination is connected in turns across an AC source and a DC source. What changes would you notice in each case if the capacitance of the capacitor is increased? So let us first draw the diagram. So we have given a capacitor which is connected with a lamp. And let us first connect this to a AC source. Now we can treat lamp just like a resistor. So this is a resistor of resistance R and the capacitor is having capacitance C. So in AC, so if we have a AC source, then the resistance offered will be root XC square plus R square. Right, so that is the resistance offered, and right, but if we connect this bulb with a DC source, then what would happen? So the capacitor will get charged and the current in this circuit will become zero. So after some time, so in this circuit, if I show the current, so if we talk about at t equals to 0, as we have closed the switch, then this capacitor will behave like a connecting wire and the bulb will be having a voltage of E around it. So the current will be maximum. So that will be E by R. So the current will decrease exponentially, right? So as the brightness of the bulb is proportional to the square of the current, so we can say the brightness of the bulb decreases and ultimately it becomes zero. There will be no brightness. But in this case, the bulb will keeps on glowing with a constant brightness, right? And the right, because it, we can say it has a fixed, if we talk about the resistance offered to the current is root XC square plus R square. So in this case, the bulb will glow. So in this case, we can say bulb will glow, but in this case, you can say bulb will not glow, right? So what changes would you notice in each case if the capacitance of the capacitor is increased? So in the first case, if capacitance is increased, so Xc, which is 1 by omega C, if capacitance is increased, we can say Xc will decrease. As Xc will decrease, impedance will decrease. If impedance decreases, current will increase. If current is increasing, then we can say the current through the bulb will also increase, so bulb will glow more brightly. So brightness will increase. Brightness will go up. But in this case, there will be no change in the, there will be no change, right? Is it clear? Now let us see the next question. An electric lamp having coil of negligible inductance connected in series with a capacitor and the AC source is glowing with certain brightness. So this bulb is glowing with certain brightness. How does the brightness of the lamp change on reducing the capacitance? Which is the similar case that we have discussed. So it's a, we can treat it just like a resistance. So the impedance will be Xc square plus R square square root of that. So this is the impedance. So on reducing the capacitance, we know that Xc is 1 by omega C. If C is decreased, Xc will increase. If Xc is increases, we can say Z will also increase. So the peak current will decrease. So as peak current decreases, the brightness will decrease. So in the first case, brightness will decrease. Right? Now let us see the second case. What would happen if the frequency is changed, right? If you're reducing the frequency. So let us see if again, Xc is inversely proportional to the frequency. Omega is 2 pi f. So we can say Xc will be 1 upon 2 pi fc. So if f is decreased, Xc will increase. Again, in this case, the brightness will decrease because current will decrease. I hope it is clear. Let us see another question. So in this case, a capacitor C, a variable resistor R and a bulb B are connected in series to an AC mains in the circuit as shown. The bulb glows with some brightness, right? How will the glow of the bulb change if a dielectric slab is introduced between the plates of the capacitor? Okay, right. So in this particular question, what is the impedance? We can say it will be Xc square plus R equivalent square, right? So we have a resistance of this variable resistor and there is some resistance of this bulb. Now if we, in the first case, if we introduce a dielectric slab between the plate of the capacitor, what would happen? The capacitance increases, that we've already studied when we were discussing capacitors. So capacitance increases. So C is increasing. As C increases, we know that XC is 1 by omega C. So C is increasing, so XC will decrease. As XC decreases, impedance will decrease. As impedance decreases, current will increase. So if current is increasing, brightness of the bulb will increase. Now let us see the second part. The resistance R is increased keeping the same capacitance. So we are not changing the capacitance. In the second part, if capacitance is not changed, it means XC is constant. If XC is constant and the resistance is increasing, we can say impedance will increase, right? Because impedance depends upon the resistance, right? So if R is increasing, impedance will increase. If impedance is increasing, current will decrease, right? So in this case, if current is decreasing, the brightness of the bulb will decrease, right? Let us see another question. A 100 microfarad capacitor in series with 40 ohms resistance is connected to 100 volts 60 hertz supply. So this 100 is nothing but the RMS value of the AC source. We have to find the reactance and the impedance and the maximum current in this circuit. So the reactance will be XC, right? Because we have a capacitor. So this will be 1 by omega C. Omega is 2 pi F. So it will be 120 pi and C is given as 100 into 10 raised to power minus 6. So this comes out to be 1000 divided by 12 pi ohms, right? So that is the reactance. Now what is the impedance? So if we simplify this 1000 divided by 12 pi, so this comes out to be nearly equals to 26.5 ohms. Now if you want to find the impedance, that will be square root of XC square plus R square. So it will be 26.5 square plus 40 square. Clear? So if I simplify this, 40 square is 26.5 square plus 40 squares root of that. Yes, so it nearly equals to 48 ohms, right? So that is the impedance, 48 ohms. So that is the answer of second part. Maximum current in the circuit. So the peak current will be E naught by impedance, and E naught will be 100 times root 2, right? Because RMS value is 100 divided by 48. So this will be, let me find this in decimals, around 2.95 ampere, right? So that is the answer of this question. Now let us see another type of a circuit, that is LC circuit. So in LC we have a capacitor and a inductor, and these are connected with a AC source. This is L and this is C. And let us say the EMF of the battery is, or the AC source is E naught sine omega t, and the instantaneous current is I, and the voltage across the capacitor is VC, and the voltage across the inductor is VL. VC naught is the peak value of VC and VL naught is the peak value of VL. So let us first draw the phasor diagram, and we know that in case of a capacitor, the current leads the voltage. So we can say I leads VC by pi by 2, and in case of an inductor, current lags the voltage. So I lags VL by pi by 2. So if I draw the phasor diagram, if this is I naught and then VL, so current lags, so this will be VL naught, and this will be VC naught, right? This will be 90 and this will be 90, because in case of capacitor, current leads, in case of inductor, current lags by 90. So the result, so we can say E vector will be the resultant of VL vector plus VC vector. So we can say E naught will be the vector addition of VL naught and VC naught, and but they are in opposite direction. So if XC, so VL naught is what? It is I naught times XL, and VC naught is I naught times XC. If XL is greater than XC, then we can say the resultant will be I naught times XL minus XC. Is it clear? Now from here, I naught comes out to be E naught upon XL minus XC. So here I have assumed that XL is greater than XC. If X is greater than XL, then then the denominator will be XC minus XL. So this is the peak current, and the denominator will be the impedance of this circuit, which is the resistance offered by this circuit, this combination to the AC current. So what is the instantaneous value of the current? It will be I naught times sine omega t minus pi by 2, right? Because the resultant, so this is basically E naught, and this is I naught, where E naught is VL naught minus VC naught. So this angle is 90 degree. I hope it is clear. So again, in this case, what is happening? In this case, the phase difference between the current and the source voltage is 90 degree, and the current is lagging. So we can call this as purely inductive, right? Circuit. If X is greater than XL, in that case, it will become purely capacitive circuit. Right, now let us see a question. A circuit containing 80 millihenry inductor and 250 millifarad capacitor in series connected to a 240 volt. So this is the RMS value, ERMS. And this is the angular frequency, 100 radian per second. The resistance of the circuit is negligible. So there is no R, only L and C is there. So it's a LC circuit. Obtain the RMS value of the current. So RMS value will be ERMS upon impedance, which will be, in this case, let us find X. It will be XL minus XC. Take the modulus of that. So what is XL? So that will be omega L. L is 80 milli. So this will be 8 ohms. And XC will be 1 by omega C. So that will be 1 upon 100 times C will be 250 milli. So that will be 400. C is 250 milli, right? Okay. 250, right? So this will be 4. Yes. So it will be 0.04 ohms. So we can say it will be nearly equals to 240 divided by 8 minus 0.04. So this is nearly equals to 30 ampere, right? So what is the total average power consumed? So we haven't covered this as of now. So once we cover average power, then I'll come back to this question. Now let us see the LCR circuit. Okay, right. So let us see. So in LCR circuit, all the three components are connected in series. So this is L, then we have C, and this is R. And there is a AC source. And let us say the EMF is E naught sine omega t. And let us say at time t, the current in the circuit is I, and the voltage across the inductor is VL, and the voltage across the capacitor is VC, and across the resistor is VR. And we can say E vector will be VL vector plus VC vector plus VR vector. So it will be the vector addition of these three vectors. So in case of an inductor, we can say I lags VL by pi by 2, and we can say I leads VC by pi by 2. And in case of inductor, there will be no phase difference. So I and VR are in phase. Now let us draw the phasor diagram. So first let me show the current. So that is I naught, and this will be VR naught, right? Let me show this with different color. So this is VR naught. Now we can show VL naught because current lags in inductor by 90 degree, and this will be VC naught. So again, I'm taking the case where XL is greater than XC. So that is the case, the resultant of VL naught and VC naught will be what? It will be in the upward direction. So this will be VL naught minus VC naught, and this is VR naught. And we have current in this direction. Now the resultant of these two vectors will give us E naught, right? And this is the phase difference phi. So tan phi can be written as VR naught upon VL naught minus VC naught. Got it? Sorry, sorry, I made an error. It is perpendicular, and perpendicular here will be VL naught minus VC naught, and the base is VR naught. So we can write VL naught as I naught times XL, VC naught at I naught times XC, and VR naught as I naught times R. So this will become XL minus XC by R, right? So from here we can find the phase difference. Now let us find the peak value of the current. So we can say, so VL naught minus VC naught square plus VR naught square should be equals to E naught square. So if you simplify this, I naught comes out to be E naught divided by root of XL minus XC square plus R square. Now this denominator is the impedance, which is the resistance offered by this combination to the alternating current. And in this case, if you look at the phasor diagram, current is lagging by phi. So the instantaneous current will be I naught sine omega t minus phi. I hope it is clear. We know the value of impedance. Let me highlight the impedance. So this denominator is the impedance of LCR circuit. It is very important formula. Do remember this. Even this derivation itself is very important. Usually you will be asked about this derivation in board exams. Now let us do some illustration from LCR circuit. So we have given series LCR. The voltage across an inductor, capacitor and resistor are 30 volts and 60 volts respectively. What is the phase difference between the applied voltage and the current in the circuit? Right, so we have given, so whatever these values are given, these are RMS values. So we can say VL RMS is 30 and VC RMS is 30 and VR RMS is 60 volt. And we know that the phase difference will be given by this. So tan phi will be equals to V L naught minus VC naught divided by VR naught, right? From the phasor diagram, we have seen this formula. And if I divide numerator and denominator by root 2, we will get VL RMS minus VC RMS upon VR RMS. So this will become 0, right? Because VL RMS and VC RMS are equal. So phi will be 0. So there will be no phase difference between the current and the voltage supplied by the battery. Let us another question. So a series LCR circuit is given where EMF of the source is given as 200 volts. So ERMS is 200 volts and frequency is 50 hertz. So omega will be 100 pi second inverse. The voltage across the resistor, capacitor and inductors are respectively 200, 250 and 250. All these values are RMS values. So we can say VR RMS is 200 and VC RMS is 250 and VL RMS is 250. Again, in this case, the phase difference will be 0, right? Okay, now let us the question. The algebraic sum of the voltage across the three element is greater than the voltage of the source. How is this paradox resolved? Okay, right. So if we draw the phasor diagram, now in this case, this is VR naught, right? This is VL naught and this will be VC naught. So the angle between VR naught and VC naught is 90 degree and between VL naught and VR naught is 90 degree. So this VC naught and VL naught are opposite to each other. So if we have to add them vectorally, not algebraically, right? So if we add them vectorally, we can say VL naught minus VC naught will comes out to be 0. Is it clear? And VR naught is nothing but 200 times root 2. And what is the EMF? So we have E naught is given as 200 times root 2. So can you see it comes out to be same. Now let us the second part. Given the value of the resistance of R is 40 ohms, calculate the current in the circuit. So we have to find the current since there is no reactance in this particular circuit because VL naught will get cancelled out with VC naught. So peak current will be given by E naught times the impedance, and the impedance in this case will become R. Is it clear? Because XL will be equals to XC. E naught is, and we have to find the current in the circuit. So if they are saying current in the circuit, you have to find the RMS value. So I will take so we will be find RMS value. ERMS is given as 200, R is 40, so this will be 5 ampere. So this is the answer of second part. Now let us see another question. So write the expression for the impedance offered by the series combination of resistor, inductor and capacitor connected to an AC source of voltage V equals to V naught sin omega t. So we know how to derive that expression, and the impedance will be given by root of XL minus XC square plus R square. Show on graph the variation of the voltage and the current with omega t. So in this case, if XL is greater than XC, then it will be you can say inductive circuit. If XC is greater than XL, it will be capacitive circuit. So if I take it as inductive circuit, then I will be I naught sin omega t minus phi. So if I show this on graph, it will look like this. So this solid line will be the EMF, right? The voltage of the source, and the dotted line will be the current line. Is it clear? So can you see there is a phase difference in this particular diagram? What we have taken capacitive circuit, right? Capacitive circuit where XC is greater than XL. So that is the graph for this LCR circuit. Right, now let us see another question. Determine the value of phase difference between the current and the voltage in the given series circuit. So we have to find the phase difference. It is LCR circuit, and resistance is given, capacitance is given, inductance is also given. Right, so now let us draw. So we have, let us say this is VR naught, this is VL naught, and this will be VC naught, and the current, peak current will be in this direction. Let us say this is I naught. Now first calculate the reactance. So XL will be omega L, and omega here is given as 1000, right? So 1000 times inductance, that will be 100 millihenry. So this will be 100 ohms. Now let us find the capacitive reactance. That will be 1 by omega C. So it will be 1 by 1000 times 2 times 10 raised to power 6. So this will be 10 raised to power 3 by 2. So it will be 500 ohms. Right? So can you see XC is greater than XL? So it means VC naught vector will be having greater magnitude in comparison to VL naught vector. So its equivalent diagram would be like this. So this will be VC naught minus VL naught, and this will be VR naught. And the resultant of these two will be the peak value of the AC source. So we have to find the phase difference. So current is in this direction, and this is the phase difference. So we can say, so tan phi will be VC naught minus VL naught divided by VR naught, and this can be written as XC minus XL divided by R XC is 500, XL is 100, and R is given as 400. So it comes out to be 1. So it means phi is pi by 4. Phi is pi by 4. Got it? So that is the phase difference between the voltage and the current. So we can say in this question, current is leading, right? Current is leading the voltage by pi by 4. Got it? Right. So now let us see what is the average power dissipation in AC circuit. So first we'll see the meaning and then the power factor, concept of power factor and the wattless current. Now let us see. Suppose we have given E, this is the EMF of a AC source, E naught sine omega t. And let us say the current in the circuit is I naught sine omega t plus phi, where phi is the phase difference between the voltage and the current. So if I want to find the instantaneous power, so we can say the instantaneous power will be given by the product of E and I. So this will be E naught times I naught times sine omega t times sine omega t plus phi. Now we can apply sine A plus B formula here to expand this. So we'll be having E naught I naught sine omega t, and this will be sine omega t plus, sorry, cos sine omega t times cos phi plus cos omega t times sine phi. We can further simplify this. So this will become E naught I naught cos phi sine square omega t plus E naught I naught sine phi sine omega t cos omega t. Now in the second term, if I divide by 2 and multiply by 2, then this numerator, this factor will become sine 2 omega t. So instantaneous power can be written as E naught I naught cos phi sine square omega t plus 2 times E naught, sorry, 1 by 2 times. This will be 1 by 2 times sine phi sine 2 omega t. Now we have to find the average power dissipation. So let us take the average value of this. So we have to take the average value of the first term and the average value of the second term. Now in the first term, E naught I naught cos phi is constant, so we can bring it out. This will be E naught I naught cos phi, and the average value of sine square function is 1 by 2 that we've already studied. And if we take half E naught I naught sine phi out, which is constant, the average value of sine function is 0. So the second term will become 0. So this will become 0 and this will become 1 by 2. So the average power will be E naught I naught by 2 times cos phi. So that is the formula for average power. Let me further write different forms of this. So this root 2 can be written as root 2 square. So we can write this as E RMS I RMS cos phi. So this formula looks like AB cos theta, right? So we can write this in vector notation. So E RMS vector I RMS vector dot product, right? Dot product of E RMS and I RMS. Or we can also write E as we can also write E as I times impedance, right? So this will be E can be written as I times impedance. So it will be I RMS square times impedance times cos phi. Let me write it over here so that you will be able to see. So it will be average power will be I RMS square impedance times cos phi. And we know that tan phi is in case of a LCR circuit, tan phi will be given as XC minus XL upon R. So cos phi will be given as R by impedance, right? So this can be written as I RMS square times Z times R by Z. So this Z will get cancelled out. So this will become I RMS square times R. Or if you want to write the formula in terms of without IRMS, so it can be written as I can be written as ERMS divided by impedance. So we have ERMS square by impedance times cos phi. So you have to remember this formula. You have to remember this formula and this formula, right? These are the three formulas that you have to remember. Now let us see the concept of power factor. So average power dissipation in AC circuit is given as ARMS IRMS times cos phi. Now this term cos phi is known as the power factors. So we can say cos phi is the power factor. In case of a purely resistive, what is the phi value? In purely resistive circuit, phi is 0. So cos phi will be 1. In case of a purely inductive, phi is pi by 2. So cos pi by 2 will be 0. In case of purely capacitive, it is pi by 2. So cos pi by 2 will be 0. So you should remember these value. And in case of a capacitive or in case of an inductive circuit, cos phi will be having a value which will be between 0 and 1. For capacitive and inductive, phi will be from 0 to pi by 2, between 0 to pi by 2, and it will be from 0 to 1. Right? Now let us see what is wattless current. So if so we know average power is ARMS dot IRMS. So I can write it like this. So this is IRMS, this is ERMS vector, right? So, and this angle will be phi. Phi is the angle between the two vectors. So IRMS has two components. So this component which is along ERMS is IRMS cos phi. And there is a component which is normal to ERMS. That is IRMS sin phi. Now this component which is normal to ERMS, which is not contributing towards the power, is known as wattless current. And this current is known as active part of current. And sometimes we can also call it as wattful current. Right? So if the question says like find the wattless current, it will be IRMS times cos phi. Sorry, IRMS times sin phi. Okay, now let us see this illustration. So when a AC source is connected to an ideal inductor, show that the average power supplied by the source over the complete cycle is 0. Right? So we know that average power is given as ERMS IRMS times cos phi. Now in case of a purely inductive circuit, phi is pi by 2 and cos pi by 2 is 0. So this will be 0. So we can say the average power over a complete cycle will be 0. Now let us see the second part. A lamp is connected in a series with an inductor and an AC source. What happens to the brightness of the lamp when the key is plugged in and an iron rod is inserted inside the inductor? So when key is plugged in and if we insert an iron rod, then the impedance, or you can say the inductance, L will increase, because L is mu naught n square A times L, and this mu, it will change. Permeability of the core material will change, so L will increase. So as L increases, inductive reactance will increase, and impedance is given as root of XL square plus R square. So if XL increases, impedance will also increase. As impedance increases, we can say the current will decrease, because peak current is inversely proportional to the impedance. As peak current decreases, the brightness of the lamp will decrease. So in this case, brightness decreases. I hope it is clear. Right, so in this question, we have given two circuits, A and B. So first circuit has only resistance and inductor, so I can say it is RL circuit. In the second circuit, we have given R, L, and C. And we have to find the ratio of power factor of both the circuits. So I'm assuming that we are connecting the same source in both the circuits. And power factor is given by R by impedance. Now for circuit A, what is the impedance? It will be root of XL square plus R square. And XL is given as 3R. So this will become root of 10R, right? So power factor for the first circuit will be R upon root 10R, so which will be 1 by root 10. Now for circuit B, impedance will be root of XL minus XC square plus R square. Now in this case, XL is 3R, XC is 2R. So XL minus XC will be 2R, right? Times R square. So this will be root 5R. Now in B, the power factor will be 1 upon root 5. And we have to find the ratio of the power factor. So 1 by root 10, ratio 1 by root 5. So this will be 1 ratio root 2. So that is the answer of this question. Right, now let us see another question. Calculate the value of additional capacitor which may be joined suitably to the capacitor C that would make the power factor of the circuit unity. Okay, let us first find the power factor of this. So here the impedance will be, and omega is given, right? Omega is 1000. So XL is 1000 times inductance, that will be 100 milli. So that will be 100 ohms. Now what is the capacitive reactance? It will be 1 by 1000 times C. So 2, and this will be 10 raised to power 6. So this will be 500. So it will be XL minus XC square plus R square. So XL minus XC will be 400 square plus R will be 400, which comes out to be 400 root 2. So that is the impedance. So the power factor is R by Z. So it will be 400 by 400 root 2. So that will be 1 by root 2. So phi comes out to be pi by 4. Now we want to make power factor unity. So what we can do? So we cannot change this 100, right? We cannot change this. So to make power factor unity, to make cos phi equals to 1, phi has to be 0, right? And to have a 0 phase difference between the current and the voltage, the circuit has to be purely resistive. To make it purely resistive, the voltage across the capacitor should balance the voltage across the inductor. So we can say XL should be equals to XC. So XL value is fixed, that is 100, right? We can alter XC value, right? So we want to have a new capacitive reactance as 100 ohms. And how we can do that? If you want to reduce capacitive reactance, we have to increase capacitance. And how we can increase capacitance? By connecting a capacitor in parallel. So we can add some capacitor in parallel. So let us find what is the equivalent capacitance. So it will be 1 by 1000 times C. So C will be 1 upon 10 raised to power 5. So I can say this will be 10 microfarad. So that is the equivalent capacitance required. So we can say we are connecting a capacitor in parallel to this, and this will be, let us say, C prime, right? So C prime plus C should be equals to 10 raised to power microfarad. So C prime has to be 10 minus 2 microfarad. So that will be 8 microfarad. So we have to connect a capacitor which is 8 microfarad in parallel to the given capacitor. Right? So that is the answer of this question. Right. So now let us move to the very important section, that is the resonance in LCR circuit. And what do we mean by the resonance? The peak current in an LCR circuit is given by E naught upon root XL minus XC square plus R square. Now we want to maximize the peak voltage or peak current. So how we can maximize? By minimizing the impedance. And how we can do that? LCR is fixed. We can only change the frequency. So we'll keep frequency such that XL is equals to XC. So when XL is equals to XC, then the I naught will become E naught by R. And this is the maximum value of the peak current for the given system. So when XL is equals to XC, we can say at what frequency we have XL equals to XC, it will be omega naught L upon equals to 1 upon omega naught C. So omega naught will be 1 by root LC. Now this is the angular frequency at which we are getting the maximum value of the peak current. And this phenomena, and this case is known as the resonance, when we have the maximum value of the peak current. Right, so now we know what is the angular resonating frequency, which is given by 1 by root LC. So if I want to find the frequency, so that will be omega naught by 2 pi, and this can be written as 1 upon 2 pi root LC. Now let us see how the impedance vary if the frequency is changed. So this is the graph. On the y-axis we have impedance, on the x-axis we have frequency, and at the resonating frequency, the impedance drops to minimum value and then increases. And if the frequency is less than resonating frequency, then the circuit will be capacitive because XL will be greater than XC. If I show you the graph of reactance, so this is the graph for capacitive reactance, and this is the graph for inductive reactance. And this is basically the resonating frequency. And here we have reactance. So we can clearly see that if F is less than resonating frequency, the value of XC is greater than XL. So we can say frequency less than FR, the circuit will be capacitive. And what does it mean? So it means the voltage is lagging behind the current. And when F is equals to R, the circuit will be purely resistive. In that case, there will be zero phase difference. And if F is greater than FR, then the circuit will be inductive. So the phase difference will be positive because the voltage is leading the current. So do remember this graph. And similarly, we can plot the graph for the current with frequency. And we know that current, the value of peak current will be E naught upon impedance. So as impedance decreases, current will increase, and at the resonating frequency, current will be has its maximum value. So do remember these two important graphs. Now let us see a question. Figure shows us a series LCR circuit with L is 10 Henry, C is 40 microfarad, and R is 60 ohms, connected to a variable frequency 240 voltage source. Calculate the angular frequency of the source which drives the circuit at resonance. So we know what is the resonating angular frequency. It is 1 upon root LC. So L is given as 10 Henry, and C is given as 40 microfarad. So 40 times 10 raised to minus 6. And this can be written as 2 times 10 raised to power minus 2. So it will be 50 second inverse, right? So 50 radian per second will be the resonating angular frequency. Now the second part is the current at the resonating frequency. So what is the current? So we can say I naught. So whenever like we have written current, right, you should always find RMS current. So the RMS current will be ERMS divided by impedance, and this impedance will be at resonating frequency will be nothing but resistance. So ERMS is given as 240 and the resistance is given as 60, so it will be 4 ampere. Now the third part, RMS potential drop across the inductor. So potential drop across the inductor will be IRMS times inductive reactance. Now what is inductive reactance? That is fine. So XL will be omega times L and this will be omega is 50 and L is 10. So this will be 500 ohms. So this comes out to be 4 times 500. So this will be 2000 volts, right? So 500 and yes, this will be 2000. So I hope this question is clear to you. So now we will discuss transformer. So what is the meaning and where we use it? What is a step up transformer, step down transformer? Then the transformer equation and what is the ideal power equation for transformer? Then what are the different losses? So we'll study these two important losses and then how we can find the efficiency. Let us see. So transformer is a device with which we can change the alternating voltage, right? We can increase the voltage or we can decrease the voltage. And it works on the principle of mutual inductance that we have already studied in electromagnetic induction, right? So let us see the construction. So in a transformer, there is a transformer core which is made up of laminated sheets. And we use laminated sheets to minimize the losses, right? In laminated sheets, the eddy currents which are being produced are not that strong enough. So there will be less heat dissipation due to eddy currents. So this is the primary winding. So on the one side we have primary winding and here we have the secondary winding. So what would happen if there is some current in the primary, due to the alternating current, this laminated core, which is made up of soft iron, will get magnetized. And once it gets magnetized, then the magnetic field lines which are being produced by the current in the primary winding, those magnetic field lines will be completely retained in the material of the core. And those magnetic field lines will be completely linked with the secondary, right? And this is how it looks in reality, right? So you must have seen such kind of a device in your surrounding in the parks, right? So that this kind of a device. Let us see. So let us see what is a step up and step down transformer. So step up transformer, we can increase the voltage. So you can say we'll be having low voltage high current to high voltage low current. And in step up transformer, the number of turns in the secondary winding will be more than the number of turns in the primary winding. So here, in case of step up, this NS will be greater than NP. And in a step down transformer, it will be, we can convert it from high voltage low current to low voltage high current. So in this case, the primary winding will be, the number of turns in the primary winding will be greater than the number of turns in the secondary winding. Okay, right. Now let us see what is the transformer equation. So let us say the flux linked with one of the winding is phi, right? So we can say, let us say it is phi p. Phi p is the flux linked with one of the winding, and it will be same as the flux linked with the secondary winding, one of the coil of the secondary winding. Now, how many windings are we do we have? So we have NP, number of winding in the primary is NP, and number of winding in the secondary is NS. So what we can do, the EMF reduced in the primary will be minus d phi p by dt. Okay, let us keep it as phi only. So phi is the flux linked with one turn. So phi p will be NP times phi and phi s will be NS times phi, right? So the EMF produced in the primary will be minus d by dt of NP times phi, and this will be minus NP times d phi by dt. Similarly, the EMF produced in the secondary winding will be minus d phi s by dt, and this can be written as minus ns d phi by dt. Since phi is same for both the winding, the rate of change of phi is also same for both the winding. So we can say from equation 1 and equation 2, we can say EP by NP will be equals to ES by NS, or we can say EP by ES will be equals to NP by NS. So the EMF is proportional to the number of windings. So do you remember this? This equation is the transformer equation, where instead of VP we have EP, right? Here we have ES. So do remember this. Now let us see the ideal power equation. So in ideal transformer, input power is same as the output power. So input power can be written as I primary times IP, and it can also be written as ES times IS. Now from this equation, we can find the ratio of the current in the two windings, IP by IS. So this will be ES by EP, and we know that ES by EP is nothing but NS by NP. So IP by IS will be NS by NP. So that you can remember, right? So here we have used 100% efficiency, so input power will be same as the output power. So now we know EP by ES is equals to NP by NS, and it is equals to IS by IP. Got it? So that you have to remember for ideal transformer. Now let us see the losses in transformer. So there are many losses, but these are two major losses: copper losses and iron losses. Let us see. What is the copper loss? It is the loss in the winding, right? If there is a current in the winding, so there will be some losses due to Joule's heating, right? And how we can minimize that? To minimize these losses, higher current coil always made up of thick wire. So with thick wire, we can reduce the resistance. And for removal of produced heat, circulation of mineral oil should be used. So we use some coolant which can take out the heat from the winding. And there are iron losses, and these are the losses which we can minimize by using laminated cores, right? So do remember this. Now, suppose if we have a real transformer which is having some losses, then we can say the power output will always be less than the power input. So we can say power output will be power input minus losses, right? So efficiency will be given by power output upon power input times 100. So this is the percentage efficiency. So power output will be power input minus losses divided by power input times 100. So we can use this relation. Right, so now let us see some questions. So why is core of a transformer laminated? So we use laminated core to minimize eddy current formations. Right, so core of transformer is laminated to reduce energy losses due to eddy current so that its efficiency can be nearly equals to 100%. Right, so now let us see a numerical. So the primary coil of an ideal step-up transformer. So we have a step-up transformer means the number of turns in the secondary will be greater than number of turns in the primary. And primary coil has 100 turns, so NP is given as 100. And the transformer ratio is 1000. Oh, sorry, transformer ratio is 100. So we can say, so in this case, NP is NS is greater than NP. So we can say NS by NP will be 100. So we can find NS to be 10,000. Okay, so the input voltage and the power are 220 and 1100 watt respectively. So we have given input voltage. So EP is given as 220 volt, and power input, which will be EP times IP, is given as 1100. So from this we can find IP, which will be 1100 divided by 220. So it comes out to be 5 ampere. So now there are 5 parts in this question. So first part is number of turns in the secondary. So we have already calculated it is 10,000. Current in the primary, it is 5 ampere. Voltage across the secondary, now we can apply transformer equation. So that will be EP by ES should be equals to NP by NS. So NP by NS is 1 by 100 and EP is 220. Now from this equation we can find ES, which will be 22,000 volts. So that is the voltage of the secondary. Current in the secondary. So, okay, right. So current will be, so in this case, there is efficiency. I'm assuming as efficiency to be 100%. So EP, IP should be equals to ES, IS. So from here, I can find the current in the secondary. So current in the secondary will be 1100 divided by 22,000. So that will be 1 by 20. So this will be 0.05 ampere, right? So that is the current in the secondary. Power in the secondary will be same as the power in the primary. So it will be 1100 watt, right? Right, so now let us see one more numericals. A step-down transformer operates on 2.5 kilovolt line. It supplies a load of 20 ampere. So basically, we have given EP, that will be 2.5 kilovolt, and we have given IP as 20 ampere. The ratio of the primary winding to the secondary is 10:1. Since it's a step down, so NP will be greater than NS. So we can say NP by NS is given to us as 10. So N, the transformer, is 90% efficient. And we have to find the output power, voltage, output voltage, and the current in the secondary. So first let us find the input voltage. So input voltage will be EP times IP. So this will be 2.5 times 20 kilowatt. So this comes out to be 50. This will be 50 kilowatt. So 50 kilowatt is the input power and the efficiency is 90%. So it means the output power will be 90% of the input power. So this will be 0.9 times 50 kilowatt. So it will be 45 kilowatt. So we know what is the output power. Now what is the output voltage? So let us find that. So by using the transformer equation, we can say EP by ES will be equals to NP by NS. So EP is 2.5 kilo and ES we can find from this equation. NP by NS is 10. So ES will be 2.5 K by 10. So this will be 250 volts. Right. So this is the second, you can say second voltage at the secondary winding, that will be 250 volts. Now we have to find the current in the secondary. So power output will be equals to ES times IS. Power output is 45 kilo and ES is 250, and from here we can find IS. So this will be 45K divided by 250. So if I multiply this 4 and this by 4, so I will get 1, that will be 180 ampere. So 180 ampere is the answer of the third part. So I hope this concept is clear to you. Right, so the last topic is AC generator. So let us see. So in AC generator, we have a conductor, a conducting coil. Let us say this conducting coil has N turns and it is placed in external magnetic field. So there is, let us say there is a magnetic field which is out of the plane. And we are rotating this coil with a constant angular velocity, omega. And the magnetic field is B. So what is the flux linked with this? So flux will be B dot A multiplied with the number of turns. So that is the total flux linked with this coil. So it will be NBA cos theta, where theta is the angle between the area vector and the magnetic field. And this theta is keeps on changing because this coil is rotating. So we can write this as NBA cos omega t. We can write theta as omega t. Now if you want to find the induced EMF, it will be minus d phi by dt, right? That we have studied in electromagnetic induction. That is the Faraday's law. So it will be minus NBA will come out, And the differentiation of cos will be minus sine, so it will become plus. So that will be omega sine omega t. So this is the maximum value of the EMF induced. That will be NBA omega. And if we want to find the current in the winding, so current can be, we can find the current will be E induced divided by the resistance. So that will be NBA omega by R sine omega t. Right? So we should know what is the value of instantaneous flux. We should know what is the value of induced EMF, and then what is the value of the current. And we should also know the graphs for these physical quantities. So if I plot the graph for flux, it's a cosine function, right? And the maximum value is NBA and the minimum value is minus NBA over one complete cycle. Similarly, if I plot the graph for EMF induced, it's a sine function. And the maximum value will be NBA omega and the minimum value will be minus NBA omega. And the last graph for the current, and the current is again a sine function. And the maximum value is NBA omega by R and the minimum value is minus NBA omega by R. And just remember one thing, when the flux is zero, at that instant we have the maximum EMF induced. Can you see? Right? So that you should remember. So here I conclude this video. So I hope whatever concept I have explained are clear to you, and wish you all the best for your exam. Thank you.